Welcome to the last unit. We're going to spend our time talking, we're going to go back to conjugation a little bit, talk some more about some pi bonds, and we're going to focus on what happens when pi bonds connect, conjugated pi bonds connect in a cyclic way, and see how that changes their reactivity. Okay. So in organic 1, we saw what happens if we have a single pi bond and we react with it. So you take Br2, and you would get addition to that pi bond, you get anti-addition, bromine, bromine. Okay? In organic 2, we saw that when you have two pi bonds and they're in conjugation with each other, you end up with a couple of possible products. You can get either this, or you can get the 1,4 addition. Oops, I lost one here. You can get 1,2 or 1,4 addition. What we're going to talk about now is what happens when the one end of the conjugated system, so here we had 4 carbons that were in the conjugated system, what happens when one end of the conjugated system meets with the other? And we've already kind of run into this a little bit because we've been using benzene rings quite a lot, and we've noticed they never kind of are part of the reactivity. That's exactly what happens here, is that all of a sudden you get this very, very stable benzene ring that does not react with Br2, and so you don't get this addition reaction or anything. And so what happens is we get this very, very stable conjugated system, conjugated cyclic system. And so that's pretty interesting. We probably want to talk about kind of when does this happen? When do we get this stable system, and when do we just get a conjugated system, and what are the differences between all of these things? Right? And so we give this thing a name. So benzene rings in general and other conjugated cyclic systems are called aromatic systems. And the name aromatic comes from before we knew about their structure. They were all kind of grouped together because they all kind of have these strong smells, which has nothing to do with the conjugated system. It just kind of is a thing, but aromatic is what we call it. And so let's look at the rules for aromaticity. And the rules for aromaticity are, 1, we have to have a conjugated system. And so this means that we can't have any neutral sp3 carbons in it. I should put this down here. No neutral sp3 carbons. Right? And the reason we don't want any sp3 carbons is neutral sp3 carbons can't participate in resonance, right? So neutral sp3 carbons break up resonance. We need resonance. And that's, with benzene rings, we can see that, right? Benzene rings have resonance structures all over the place because we can move those 3 pi bonds around in the ring, right? We can move this one up here, this one over here, this one over here, and we get another benzene ring. These two are resonance structures of each other. They're the same compound. We don't really have to ever draw both of them. We understand that although we draw it one way, the other way is also possible. But notice that there are no neutral sp3 carbons in here. If we try to draw a 7-membered ring, right, now we have this neutral sp3 carbon. A carbon that doesn't have any double bond character, it doesn't have any charge, and so it can't participate in resonance. And so we can't draw a resonance form where we move these pi bonds around, because if I tried, I would move this pi bond here, I move this pi bond here. I can't move this pi bond up here because this sp3 carbon already has 4 bonds. I can't add another bond to it. And so the only thing I can do is make a charge here. But notice that that means that I can't flow the electrons through the entire conjugated system. This is just a conjugated system, conjugated, but it's non-aromatic. And so we already have kind of two categories. We have conjugated, we have aromatic systems, and we have non-aromatic systems. And non-aromatic systems are conjugated systems that don't connect the two ends of themselves, right? Don't connect in a cyclic way, usually because of neutral sp3 carbons, right? So for example, a 5-membered ring would also, right, if we just look at carbons, this would also be a non-aromatic system because we have this neutral sp3 carbon here at the top of the 5-membered ring. So the resonance here would not be. We can still do 1,2 and 1,4 addition, right? All of those things can still happen. We can do our regular double bond reactions, but we can't do, this doesn't become aromatic. And so this does not get the stability, right, that aromaticity gives us. So aromatic systems are very stable. Non-aromatic systems, conjugation still gives us some stability, but they're just kind of our garden variety organic compounds, right? And so stable, but nothing special. Right. Okay. So aromatic systems are things like benzene, right? Here we can see the conjugated system connects with itself, right? If we start numbering here at 1, right, the other end of that conjugated system ends up being right next to, connected back to carbon 1, right? So aromatic compounds are cyclic conjugated systems. And that seems pretty straightforward, except that it's of course not that easy, because if we look at cyclooctatetraene, right, this is a cyclic conjugated system. This compound is incredibly unstable. And so we say, all right, so what's the difference here? The reason that this one is unstable, it goes into, we have to kind of talk about where the electrons are in the orbital, but we give this a name. There are cyclic conjugated systems that are very unstable. We call these anti-aromatic, right? So we should put that on our list. Anti-aromatic systems are very unstable. Right, so non-aromatic systems, so non-aromatic versus anti-aromatic. Non-aromatic are conjugated systems that are not cyclic. Anti-aromatic systems are also cyclic conjugated systems. All right, so why is this 8-membered ring unstable when the 6-membered ring is so stable? Stable and aromatic. So this took a while to kind of figure out, and what we figured out once we got into quantum mechanics, we started to look at, okay, so each one of these pi bonds, so this has 4 pi bonds, bonds, and that means it has 8 pi electrons, right? Each pi bond has 2 electrons. This one has 3 pi bonds, and thus has 6 pi electrons. What we figured out is there's kind of like magic numbers. Some numbers lead to aromatic systems. When you have the right number of pi bonds and the right number of pi electrons, that number leads to aromatic systems. Some numbers are the wrong number of electrons, and you end up with anti-aromatic. And what they figured out, and one way we can do this is you can use frost circles. And what they said is, okay, if we fill in the pi orbitals, we start with 1 pi orbital, and then we go up. So this one has 8 pi orbitals, right? If we fill this with electrons, so going back to our quantum mechanics from Gen Chem 1, right? If we fill this in with electrons, we put 2 in the lowest energy orbital, and then we fill in the next orbital, we fill in 1 and 1, and we still have more electrons, so we fill in 1 and 1. That's 6 total electrons, but when we move up to the next level, right, we have unpaired electrons. We put 1 and 1 there and there. And so because we have 8 pi electrons, we end up with these unpaired electrons, which is going to make this thing unstable, right? Think back to radical reactions, right? Unpaired electrons or radical reactions, those are unstable. And what turns out is anytime you have 8 pi electrons, because of the way these molecular orbitals line up, you have one low energy one, and then they kind of pair themselves as they go up, you'll always end up with unpaired electrons. So 8 pi electrons is just bad news. It always gives us unpaired electrons. 6 pi electrons goes much better. 1, 2, 3, 4, 5, and then 6, right? 2 electrons in the bottom, and then 3, 4, and then we have enough to go back and pair these up. All electrons are paired. This makes this stable, right? So you can go through and for any number of electrons, you can draw out the orbitals. You'll always have one orbital at the bottom and then pairs of orbitals going up, right? This one has 6 pi orbitals, right? Because we have 6 carbons in the ring, right? You can figure all of this out, right? What you'll notice pretty quickly is that there's a pattern, right? And the pattern is that if you have the number of pi electrons is divisible by 4, you get an anti-aromatic system, right? So when we count these up, we look at the number of pi. We have 4 pi bonds. We have 8 pi electrons, and so that means that we're going to end up with 8 pi. 8 is divisible by 4. That means that this is an anti-aromatic system. The aromatic systems will have numbers of pi electrons. Oops. We'll have the number of pi electrons not divisible by 4. So the number of if the number of pi electrons is not divisible by 4 and you have a cyclic conjugated system, you get a very stable aromatic ring, like the benzene ring. If the number of electrons is divisible by 4, you get an anti-aromatic ring, which is going to be very unstable. Right? And if you have neutral sp3 carbons, then you don't have a complete cyclic system, and you no longer have either anti-aromatic or aromatic.